So this is the Michaelis-Menten equation. So you could rewrite the Michaelis-Menten equation, and it's fine if you did. If you wrote it as V is equal to K cat times E times S divided by Km plus S, it's the same thing. Because Vmax is just specifically this catalytic rate constant times the enzyme concentration if known. It's just that many times, especially in vivo, we do not know the exact concentration of enzyme. If you do not know the exact concentration of enzyme, then you have to use Vmax, okay? Which still can be descriptive, but it's not as descriptive as exactly knowing Kcat. All right, so what shape of curve is Michaelis-Menten? Because this is the y, this is the x-axis, is s. And so, what shape will that give you? It's hyperbolic. Okay. So it's going to look something like this thing is in the way. It's got like a mind all of its own. It's attacking me. All right. Something like that. Okay. And when we last left off, we were talking about the limits, like what happens whenever S gets really, really, really large, then it simplifies. And it simplifies, so this is when S is really large, so it's much, much bigger than Km. This simplifies to where we have V, is equal to Vmax times S over what would be S, essentially, because it's so much bigger than Km that Km is minuscule. And then what happens, of course, is the S's cancel, and so we get that V is equal to Vmax. And that's just a fancy way of saying, on this curve, and this is the important part, you need to know that the asymptote with which this approaches, that's Vmax. That's as fast as it will ever get, okay? And I'll try to use a more common world way of explaining it in just a moment. Okay, then we went to the other extreme, and that was when S is really, really tiny. And so now it's much, much, much smaller than Km. Then this still simplifies to where we have Vmax. V is equal to Vmax times S over Km. Okay, because Km plus S, Km is so much larger that the S is negligible. And so what that does is, since that's this portion of the curve, and this is where I have problems trying to draw it. Whoops. You can imagine, not too shabby, like the tangent, remember that's called the tangent from calculus? Okay, the tangent as it goes towards 0, that's the slope there. So let me change colors. The slope of that line right there, so the M, would be equal to Vmax over Km. That's actually very important in a moment. Okay, and I'll explain the reason why that's important. So there's a couple of other terms that we're going to learn. Kcat is the catalytic rate constant. It also has another term that gets used many times called turnover number. Okay, so let me just scoot all that up. So Kcat is also called the turnover number. Okay, that's technically, mathematically what they'll tell you is that sets the limit at all first order rate constants for the entire mechanism. You could have 150 steps, to that pathway, and that would set the limit. You can never go beyond that. Which, if you think about it and then that's kind of difficult to think about, but when you think about the Vmax, it's related to Vmax in the sense that Vmax is that number times enzyme concentration. You can never get faster than that. That's what it means by it sets that limit. Okay. Km It's called the Michaelis constant. Many times, people erroneously state that that's the dissociation, that is KD, but that's only KD under very, very short, under very specific circumstances. So we'll talk about what we use KM for. Then we have a term which actually is the one that's the most difficult for people to grasp. It's probably the most important, and that's Kcat over Km, or Vmax over Km, because once again, you have to use Vmax over Km when you don't know the enzyme concentration. If you do know the enzyme concentration, they call it Kcat over Km. And this right here, like I said, is very important because this is the specificity constant. Or they also like to call it the catalytic efficiency. Now, I'll explain what that means in just a moment. Because in this entire chapter, these are probably the absolute most important things to understand. How to look at Michaelis-Menten curves and understand these terms. And then once we start talking about inhibitors, hopefully it'll help you understand the way that it affects these terms. Okay. Using terms like Vmax over Km, those are really nebulous and kind of difficult in order to understand. So let's think about your enzyme. You can imagine it, since all it does is it takes a substrate, it puts out a product. So I used to live in Detroit. So Detroit is known for a couple of things. That's one thing that the city of Detroit's probably most well known for. Cars, okay? The other is Motown music. It's easier to explain this with cars, okay, than it is Motown music. I'm sure I can come up with one. All right, but you can imagine that enzyme being like a car factory, right? Because all it is the factory itself is unchanged, but it takes in a substrate, takes in resources, and puts out a product, which is that product being cars. And so it's going to have a rate, so many cars per day. So let's just do an example. Or actually, we're going to do one generic example. Or what? Why do I do the generic? Let's do. I'm probably going to run out of room because this is kind of narrow. So on here, we're going to have V, and that's true for all of these. I'm only going to put the units on the one in the middle because I don't have enough room on the two side ones. But for the velocity for our enzyme car factory, it's going to be the number of cars per day. Of course, for the enzymes, we're usually talking about it's going to be concentration of product per unit time. So things like molar per second or maybe millimolar per minute or something like that. But it's going to be some type of concentration per unit time. And of course, with our cars, we're going to be talking about our resources. And here, we're going to say instead of saying substrate, we're going to say dollars. Because if I use money, people understand it so much better. Okay, and now we're just going to end. This is not saying that I'm putting any, in fact, since I'm making it up as I go along, I'm not saying that one car company is better than another car company. But let's just say that we've got Ford. What's another car company? Toyota and Honda. Okay. And they're all, with all three of these, you're going to start off with, if you put no money in, you're not going to get any cars out, okay? And at some point in time, your enzyme, or car factory, is making every assembly line in it is just as busy as it will ever be. So you can't make any more cars. All your workers are going as fast as they possibly can. So they're all going to look like that. Sometimes, maybe it's really steep. Maybe it's really... That's supposed to go on, and you can't see, but it's level off. Okay, here, let me redo that one because that's not a very good one. All right. So all three of them is going to have a Vmax, the maximum number of cars that they can make in a single day. Okay, so I'm going to be making this not, I'm going to try to keep numbers where I can do it mainly in my head. So we'll say that this is for Ford, it's 100, so that's our Vmax. So here we'll do this. So Vmax for Ford was 100 cars per day. Toyota, we'll say that Toyota, the scale, this is going to be a different scale, but let's say that perhaps Toyota can do only 50. Maybe that's 50 right here for its Vmax. $50 cars per day. And then then Honda. And Honda, maybe their factories is not as big or what have you, but we'll say that theirs is at 25. So that's their Vmax. Oh, let me change colors. KM, literally, it's technically the constant, and I forgot to show this on the previous curve, but mathematically, what it means, so you guys have your notes. So here, I'm going to go ahead and skip ahead. You can go back in your notes. I can't, so I'm going to go show you another picture, and then we'll come back. All right. Now we're back. Oh, okay, so Km, what that means, that's the concentration of substrate. So remember, that'd be the concentration, or how many dollars it takes to get exactly 50% of Vmax. So on here, we would go to 50. Oh, whoops, I'm using the wrong color. We go up here, we go to the number 50, because that's 1/2 of 100. You go over to where it hits the function, if you think back to calculus, and you go down. So that is the Km. And I'll say, and I'm making this number up. Obviously, I didn't put a units on this, I mean the number line on this one. But let's say that for Ford, that was, let me redo it. I'll say $20. It's supposed to be a dollar sign. Likewise, since the Vmax for Toyota was 50, we go to 25. We go over, and we go down. So this right here, that would be the Km. And let's just say, because I want to keep the math really simple since I don't have my calculator here. And I'll say that, for example, what if that Km is $5? So we would say, okay, that's $5. And then finally, for Honda, we would go to 12.5, since its Vmax is 25. We go over, go down, that would be its Km. And let's say that for it, it's, I don't know, we'll say it's $10. Once again, I'm not making a political statement of any sort here, or an economical statement. So my question for you here is, of these three, which one, if you have unlimited resources, which one of these is the fastest? Is it going to be Ford, Toyota, or Honda? Which one's going to be the fastest at making cars in a day? Ford. I mean, because it says that you can make 100, so it's fast. Now the question is, which one is if you were an investor, which one is the most efficient? That's the calic efficiency. Well, just because something is fast or something is slow or slower, it doesn't necessarily mean it's really efficient, right? So we have to have another term. So that's where we get that term Vmax over Km. Which once again, if you were using a computer program to do this, it would literally find the tangent of the curve at the lowest point and all that kind of stuff. I'm sorry, the slope of the tangent of the curve as it approaches 0. But we can literally just take 100 divided by 20, and 100 divided by 20 is 5. So that literally means it takes that Ford can do 5 cars per day per dollar. Whereas Toyota, 50 divided by 5 is 10. Okay, so that's 10 cars per day per dollar. And then finally we have Honda, and it's 25 divided by 10, which is 2.5. 2.5 cars per day per dollar. So now, of these three, if you were an investor, which of these three would you want to put your money into? Which one's the most efficient? Is it Ford with 5 cars per day per dollar, Toyota with 10 cars per day per dollar, or Honda with 2.5 cars per day per dollar? It's Toyota, because Vmax over Km is that catalytic efficiency, or the specificity constant. It just tells you how efficient. It may not be the fastest enzyme. Sometimes it is. Maybe the fastest enzyme is the one that's going to be the most efficient, but maybe it's not. Sometimes, if you think of Km as being the affinity that it may have for a substrate, sometimes something has a really low Km, which this one does. But for example, if we compared Ford versus Honda, Honda apparently has a more of an affinity for its substrate because of the fact that the Km is lower, but Ford is more efficient overall. And the reason why is because it's faster, right? That's why this takes into account how fast it is, plus its relative affinity for substrate. So you can either use an enzyme and compare multiple substrates if it's a promiscuous enzyme and determine which one is the best substrate, or the most efficient substrate, or you can take one substrate and compare different enzymes. They do this a lot of times whenever people hear about mutations, or maybe there are different isoforms. It's because, they're just different versions of the same enzyme. But one of them may have a higher affinity, or be more efficient, I should say, with making product than the other enzyme, or the other form of the enzyme. So that's why number is so important when you think about how efficient something is, an enzyme is. This term right here is important, which is telling you how fast. But just because it's fast, it may not be efficient. Or just because it's slow, it may not be inefficient. And then this term right here, Km, gives you an apparent affinity for the substrate. Technically speaking, mathematically, if you did all this, it's literally the affinity for all enzyme-bound intermediates. But it gives you a relative idea of the affinity. But just because sometimes you can bind something too tightly, and so it becomes more inefficient because it just likes holding onto the substrate. Or it could bind too loosely. Okay. So this was the Michaelis-Menten, because I forgot to point this out. That's V is equal to Vmax times S over Km plus S. Okay, and we talked about when S was really big, and we talked about when S was really tiny. But what happens when S is equal to Km? Okay, so I forgot about that one. When Km is equal to S, then what happens is V becomes Vmax times S over S plus S, which is the same thing as saying Vmax times S over 2S, right? Well, this simplifies. What's going to simplify there? It's going to be the S's cancel. I have a S on the top and S on the bottom. And so this becomes V is equal to Vmax divided by 2. So literally what Km is it's a concentration of substrate where rate is exactly 50% or exactly 1/2 of Vmax. So that's why you can write that in as a little side note or something earlier in your notes. Because then we'll talk about what that means on our little car chart in just a moment. So I'm going to go back. Hopefully it'll let me go directly back. Which would be really interesting, because I'm not sure how this program handles recording going frontwards and backwards. All right, so that's why this is just really important. The next few slides actually literally just go through Michaelis-Menten and equation, and so that's why I'm going to go fairly fast on these, because we've already covered this. We worked it all out ourselves. Okay, we get the Michaelis constant, which is Km. It's literally the substrate concentration, which the reaction, so the rate, is equal to 1/2 Vmax. If it's a low Km, remember, if it's a low Km, that means it has a higher affinity, or it would have a higher apparent affinity. So a lower Km usually means it's binding tighter. Okay, and then Vmax, I don't know why that V is not big, but it should be a capital V. Vmax is equal to Kcat times E. If you know the enzyme concentration, then we can talk about everything in terms of Kcat. If you don't, we have to use Vmax. Okay, which a lot of times in vivo they'll use Vmax because it's not like you can tell the exact, many times you can't tell the exact concentration of an enzyme inside a cell, for example. I actually think this is an ugly curve. Okay, so I do expect you to be able to tell on the curve here where Vmax, Km, and Vmax over Km are. Vmax is that asymptote. I think they got a little liberal with it where they said it was. Km, once again, what you do is you go to 1/2 that spot, you go down, and you hit where the Km is. Km is literally the substrate concentration. And then the Vmax over Km on this, what you do is you draw the tangent down there at 0, and you say that the slope of that is equal to Vmax over Km. Okay, back in the old days, they used to have to, when they would write journal articles and stuff, they would have to do everything by hand. They didn't have all the computers, so they'd have to do everything by hand. And it was hard to draw in hyperbolic curves and to draw it well. You can imagine, they didn't have the computers and everything. And so, and I don't know if you learned this in calculus or if you did and you forgot it or what they stress, but there are ways to take a hyperbolic function and turn it into a line, to a straight line. Okay? And so what they do here, and they used to do that because people could think better in straight lines. So it's easier for you to draw, it's easier to understand error and things like that by looking at a straight line. So I'm just going to read, this is just Michaelis-Menten, so V is equal to Vmax times S over Km plus S. Nothing new. But what you can do is you can take this Michaelis-Menten, which is hyperbolic, and the way to turn it into a straight line is you do what's called a double reciprocal. And I don't know if you remember this from calculus or not. So what that does is normally, this is y and this is x, and it looks like this. If you do 1 over y, and you plot it versus 1 over x, it'll look like this. Oops, that's supposed to be a straight line. It's not too shabby, but it's supposed to be a straight line. It transforms it and turns it to a straight line. Okay. So now we're going to prove that using the Michaelis-Menten, and the reason why that's important, which will hopefully becomes more obvious. So if we go back to Michaelis-Menten, it's going to become 1 over V is equal to Km plus S over Vmax times S. And you think back to just the rules of fractions, you can separate things that are on top, but you can't on bottom. Okay? And so what I mean by that is this becomes 1 over V is equal to Km Vmax times S plus S over Vmax times S. But these are concentrations, but it's easier for me to draw parentheses than it is to draw a square bracket. So please give me that creative license there. But we can actually simplify this. So we have an S on the top and we have an S on the bottom. So this entire term here, now I will rewrite it, but it will become 1 over V max. We can't do that on the other one, okay, because we don't have an S on the top. But I can write it just slightly different to where it now becomes 1 over V is equal to Km over V max. I just took that part out, times 1 over S. Because whenever you multiply those together, you're going to get Km over V max times S plus 1 over V max, because that's where we simplified it. I'm just going to move everything up, if you don't mind. So why did I do that? Oh, and this, by the way, because I forgot to tell you, is called the Lineweaver-Burk equation that we just derived. It's really the Michaelis-Menten. All they did was they came around, they took a double reciprocal of it. They were the first ones supposedly that did it, so they get it named after them. Oh, and Burke actually may not have an E on the end. I don't remember if it's the traditional Burke or not. But you know, poor Michaelis-Menten, you know, they come up with a really hard one, and then you just have people like, oh, what if we just take the double reciprocals and it draws a straight line, and they get to still the glory. There are others too. There's Edie Hofstee. There's Edie Hofstee's the other one that's really popular, where all you do is you take Michaelis-Menten and you multiply it by things, and you just rearrange it, and it turns it also into a straight line. Okay, so the way that this will look, whoops. So now we plot 1 over V as a function of 1 over S, because it's a double reciprocal plot. And you're going to get something that looks like this. Okay. Oh, it's going to be a straight line. I just have problems drawing a straight line. Oh, that's not too shabby. Now I want to point out a couple things. So first of all, it's just easier for people to comprehend straight lines, you know. They may even show it drawn like, well, I'll leave it at that. Okay. So I want to point out a couple things. The y-intercept, which if you think back to algebra, that's when the concentration of substrate is equal to 0. So this up here, I'm sorry, that's when x is equal to 0. So if that's 0, all of this cancels out. So the y-intercept there, which is what, y equals mx plus b, the b is equal to 1 over v max. Likewise, the slope, and I deliberately wrote it this way, see it's y is equal to m times x plus b. So the slope of this line, the m part, is going to be the inverse of your specificity constant. And if you figured up the math, like you can go through on your own and figure it out, to where if you take this all the way out here to the x-intercept, the x-intercept is going to be equal to -1 over km. Okay, so that's one of the reasons why people liked the Lineweaver-Burk, is it makes it really nice. And we're going to talk about in the next lecture about what happens once we start talking about inhibitors. So there are different types of inhibitors. There are 3 main classes that you need to know. There's a competitive, non-competitive, and an uncompetitive. And then you can have a mixed, which just means it's a mixture of any of them. And so we'll talk about what that means on the next class, and also what that would look like on Michaelis-Menten and the Lineweaver-Burk graphs. Okay, so I'll go ahead.